stereochemistry problems. They're kind of fun. It's a departure from reactions, you know, gets you thinking in a different way for a few minutes. Okay, so let's take a look at these two questions. We'll start with number one, and it just asks us which one of these molecules has an R configuration. Okay, I'm going to go through these not super slow because we've gone over stereochemistry many times. If you don't understand or if you need me to repeat something, just let me know. Okay, we start with A. The hydrogen is in the back. That's good. We look at the groups. We have oxygen as highest priority. The carbon that is attached to oxygen is going to be second highest. And then the methyl is third. So we're going like this. That's reverse. So this is S. If we go over to B, the hydrogen is in the back. So that's going to be the lowest priority group. The oxygen is number 1. The carboxyl group is going to be number 2. And then we have this CH2OH, which is going to be number 3. We're going like this, which is also reverse. So that is, or counterclockwise, I should say. So that's S. If we go to D, we look at D. So we have the hydrogen in the back. It's lowest priority. We have the oxygen as 1. We have this nitrile, which is 2. And then we have the methyl as 3. It's going counterclockwise. So it is also S. You can see where I'm going with this. And the very last one in C. So I'll use my red pen again. Now there's no hydrogen attached directly to the stereocenter, but you see that the oxygen is going to be number 1. The carboxyl, this group, is going to be number 2. This group is going to be number 3. And now the lowest priority group is actually a methyl group. This one happens to be the lowest priority. So this is number 4. We're going from 1 to 2 to 3, which is clockwise, and our lowest priority group is in the back. And so this is the only one that is R. And so the correct answer is C. Thumbs up if you got that one. Did anybody get that one? I'm sure somebody must have gotten it. I'm sure you all got it. Fantastic. That's a good feeling. That's a good feeling because stereochemistry is not easy. If it was easy, anybody off the street would be able to do it. Question number 2, the absolute configuration. You got 2 chiral centers. We'll start with the one on the left. On the left, we have the hydrogen atom front. It's going to be the lowest priority. So we're going to put a 4. What the heck is D? Okay. Could anybody answer that for me? What does D represent? Does anybody know what D stands for? We mentioned D in the chapter on NMR. Anybody tell me about D? Yeah, it's deuterium. So deuterium is just an isotope of hydrogen, except there's a neutron in the nucleus. So it would have a higher priority than hydrogen, right? So this must be number 3, right? Because it's just slightly higher than hydrogen because it has a higher mass. And then here, this carbon is attached to a sulfur, an oxygen, and a carbon. I'm listing them in order of their atomic number, starting with the highest. And C6H5, so C6H5 is this. It's this. So that is a phenyl. Phenyl. So what we're saying is, you know, what is this carbon attached to? That carbon is attached to carbon, carbon, carbon. And therefore, this carbon would be the first highest priority, and this would be the second highest priority. So we're going from 1 to 2 to 3, which is counterclockwise, but the hydrogen's coming out in front. So instead of S, this must be R. So the answer is either A or D. We can cancel those ones out. Now I'm just going to erase this. We're going to scribble all that out. And we'll take a look at the stereocenter on the right-hand side. So if I look at this, the highest priority is going to be the sulfur. Second highest priority is going to be the oxygen. We see that this carbon is attached to a carbon and a deuterium and a hydrogen, whereas this carbon is only attached to 3 hydrogens. So the methyl group must have the lowest priority, and this group must have the third highest priority. I'm going from 1 to 2 to 3. I'm going clockwise, and my lowest priority group is in the back. Therefore, this stereocenter is also R. And just like that, I've got the right answer. It's R and R. Cool. There we go. All right, let's move on from there. So that is question number 2. Let's move on to question number 5. Put a bunch of stereochemistry problems in here. Hey, question number 5, just to, do you remember what meso is? What was our definition of a meso compound? It's a compound. Meso means you've got 2 or more. Everything that we see always has 2, but 2 or more stereocenters. Stereocenters with a plane of symmetry. So which one of these 3 compounds fits that bill? I mean, one has a plane of symmetry in it. There's no doubt about that, but it's got no stereocenters. So we can cross out A and D. If we look at, let me just ask you, I'm going to skip number 2 for now. Is there a plane of symmetry in number 3? I'm talking about a plane of symmetry. I'm not talking about an axis of symmetry. Is there a plane of symmetry in 3? Can anybody? Exactly. The answer is no. There's no plane of symmetry in 3. There's an axis of symmetry. Yes, I agree that if you were to put a line through here, and if you rotated that 180 degrees, yes, you would see rotational symmetry, but there's no plane of symmetry. Therefore, this cannot be a meso compound. So we can cross out 1 and 3. The only answer is 2. It's the only one. Now, it's difficult for me to show it here, but the plane of symmetry runs from the carbon in the back right into the middle, like that. So this is a stereocenter, as is this, but since there's reflectional symmetry, a plane of symmetry, those 2 stereocenters cancel each other out. Give me a thumbs up if you follow me on the concept of meso. And if you have a question, do not hesitate to ask me. Okay, so that's a little review on what meso compounds are. We've got 2 or more stereocenters, but you've got a plane of symmetry in the molecule. Good. Okay, so that's question 5. Let's move on to question 7. Oh boy. Now this one, I want to go over this one with you. It's just more practice.
I'm sorry, but
go ahead. Yeah.
just kind of have a question. So I
Sure.
kind of confused between the plane of symmetry and axis of symmetry. What's the difference between them?
Yeah, so let's go over it. So let's take a look here. If I draw it. So if I draw compound number 2 and compound number 3. So if we look at them straight on, compound number 2 would look like this, right? Where you have a chlorine going up and a hydrogen going down, and a chlorine going up and a hydrogen going down. And in compound number 3, I don't remember which side the chlorine was going up, but you've got one going up and then you've got one going down. Okay, are you with me on that so far? This is compound 2 and 3, except now I'm just drawing it so your eyeball is looking at it, straight on, looking at it that way. Okay, all right. So we can see that there is a plane of symmetry, right? If I take a ruler and I draw a line through this compound here, I take my red pen and I draw a line through here, you can see that there is a plane of symmetry over here. But if you do the same thing here, there is no plane of symmetry in number 3. There's no plane of symmetry here. However, if you were to rotate around this axis 180 degrees, okay, I'm just going to put a star on this chlorine here. What you would end up with is something that looks like this. It would be the exact same thing, but now the chlorine that has the star would be down here, right? And the other chlorine would be the one pointing up, but there's no way for you to distinguish between these 2. So this is what we call rotational symmetry, rotational, and this is a plane of symmetry. Does that help?
Yeah, thank you. That helps very much.
Yeah, no problem at all. I like explaining things, so never hesitate to stop me for an explanation. All right, you've studied enough organic chemistry by now. You deserve an explanation for anything that you're not 100% sure on, so don't hesitate to stop me. Where the heck was I? Somewhere down here. Okay, so we covered question 5. Let's try some more stereochemistry. Get some more practice. Question number 7, I think, is a good one. Okay, I wanted to go over this question with you. This is a carbohydrate. So, and I know that many of you are interested in taking, well, many of you have to take biochemistry for your degree, but I know that several of you are just expressed an interest in biochemistry in the future, and that's good. So at the very end of organic chemistry 2, we touch on biochem. So we'll talk about carbohydrates and stuff. But I just wanted to review how would you figure out the configuration of a stereocenter in a carbohydrate? So let me show you. Remember that when you have a Fisher projection like this, and I'm going to erase this in a second, but any bond that's horizontal is coming out towards you, okay? It's on a wedge. This is on a wedge. This is on a wedge. This is on a wedge. Any bond that's vertical is on a dash, okay? Anything that's vertical is on a dash. So the conclusion to all that is this. If I'm trying to evaluate the stereochemistry of this stereocenter, okay, stereocenter 2, since a hydrogen has the lowest atomic number and it's horizontal, that means that whatever I get, whether it's whether I'm going clockwise or counterclockwise, I'm going to reverse it because my lowest priority group is coming out towards me. And that's one of the little tricks I taught you. So if we just focus on carbon number 2, I'm going to erase this for now, okay? But look, the oxygen is going to be number 1. This carbon is attached to oxygen, oxygen, hydrogen. This carbon is attached to oxygen, carbon, hydrogen. This is my tiebreaker. So this is carbon number 2. This is carbon number 3 down here. So then I go around my stereocenter. This carbon, I go from 1 to 2 to 3. That's going counterclockwise, which would be S, but since the hydrogen is coming out towards you, you reverse it. And the stereochemistry of carbon 2 is 2R. So that means we can scratch out C and D. Now we're going to do the exact same approach to carbon 3 to figure out the stereochemistry there. Let's do it again. Okay, so carbon number 3. I have, this is going to be lowest priority for sure. It's the lowest atomic number in the entire periodic table. This is going to be the highest. Son of a gun, where did I go here? Where was I? There we go. All right, back to it. So carbon number 2 is attached to an oxygen, carbon, and a hydrogen. Carbon number 4 is attached to an oxygen, hydrogen, and hydrogen. This is my tiebreaker. This is carbon 2. I'll just circle that. And this is number 3 here. So I go from 1 to 2 to 3. I'm going counterclockwise, which would be S. But since my hydrogen is coming out in front, I reverse it, and it's 2R, 3R. Give me a thumbs up if you follow me on that one. Remember that if the hydrogen is horizontal in a Fisher projection, you're always going to have to reverse it. And do you want me to show you a rule of thumb? I'll show you a quick rule of thumb that we go over in organic chemistry 2. Is that when you have a carbohydrate and you have the most oxidized carbon at the top, like that's the most oxidized carbon in the whole thing. And I know we haven't covered oxidation states yet. That's an organic chemistry 2 subject. However, whichever carbon has the most bonds to oxygen is the most oxidized. Any hydroxyls that are on the right-hand side are R, and if they're ever on the other side, they're S. So that's kind of a shorthand that I teach you in organic chemistry 2. And it's not till the very end of the class. But anyhow, just to put that bug in your ear. Excuse me. All right, where was I? Let's take a look at, that was question 7. Let's try question 9. A lot of good stereochemistry questions in here. Ooh, this is a good one because it brings reactions into it. Mr. Dion likes reactions. It says, what would be the stereochemical classification of the product of this reaction? So you're taking 2-butene. It doesn't tell you if it's cis or trans, so it must not matter. So let's just write out the trans because it's going to fit better. And then we're adding HBr to that. What are we going to get? Are we going to get RS, a meso compound, or a racemate? Could anybody answer this before we even tackle it? Just adding HBr across an alkene. What would we end up with? We looked at this many times in chapter 8. So this would be a chapter 8 thing. Well, let me ask you a question then. Is this going to be a Markovnikov addition or an anti-Markovnikov addition or neither? In this specific case. Exactly. Luke and Coy, you're both 100% correct. They just both said no, it's neither, Mr. Dion. Both of those carbons have one hydrogen attached to them. So there's no Markovnikov or anti-Markovnikov to even consider here. So let's just draw what the intermediate would look like. Right? This is just hydrohalogenation. Hydrohalogenation. Just classic here. So we're going to do the protonation, and then we're going to end up with this intermediate where we have a carbocation. What's the molecular geometry of a carbocation? It's trigonal planar, which means it's flat. So if it's flat, that means that when the bromide attacks, the bromide can come in and it can attack from the back face of the molecule, or it could attack from the front face of the molecule. That means that you're going to end up with this compound where the bromine is in the back, and you're going to end up with the bromine being in front. So this is a pair of enantiomers, and therefore it's going to be a racemic mixture. So a racemate is the same thing as racemic mixture, a racemate. They both mean the exact same thing. Yeah, there we go. Everybody, thank you for participating in the chat. By the way, I love it when my students write answers in there. I don't care if it's right. I don't care if it's wrong. I just like it when my students answer questions. It's always fun to kind of interact. Question number 10. Remember the whole day I spent talking about cyclohexane? Remember that? We did a whole day. I had the models out. It was in chapter 4. So chapter 4, we spent a whole day on cyclohexanes, and I went over 1,3-diaxial interactions and flipping the ring. Well, all of these compounds are diastereomers of one another. Could anybody just eyeball these and tell me there's one that's more stable than all these? Could anybody say which one it is? I'm not a speed guy, but this is a question I would expect you to answer pretty quickly. Thanks, Michelle. Great. Right. You know, why was Michelle able to answer that so quickly? She just said, well, look, Mr. Dion, everything else has something, you know, that's, or multiple things that are axial. B is the only compound where let's write it here, all substituents are equatorial. There you go. So that's the answer, right? The problem with these kinds of things is that you get these 1,3-diaxial interactions, right? With everything that's axial, and that creates a steric hindrance, which decreases its stability. Perfect. Excellent. Excellent work. Okay, let's try another one. Oh boy, we might have to go to a piece of scratch paper for this one. Question 11, more hydrohalogenation again. It just asks you, you know, what's the product of this reaction going to be? So this is hydrohalogenation. This could be a chapter 8 thing. You're taking this and you're adding HCl to it. So in this case, you're going to have a Markovnikov addition, aren't you? So if I put a red carbon here and a green carbon here, can anybody tell me where the hydrogen is going to go? Is it going to go in the green carbon or the red carbon? Would the hydrogen go on the red or the green carbon? Yeah. Yeah. My students are saying it's going to go in the green carbon, and that's correct because this is a Markovnikov addition. And so we're going to end up with an intermediate. I'm not going to draw the mechanism, but you're going to end up with an intermediate that looks like this. Okay, and then the chlorine can come in and it can attack. And so you're going to end up with this, where you have the chlorine here. Is there a stereocenter in this molecule? The answer is no. There is no stereocenter. Stereocenter. And if there's no stereocenter, we would say it's not a mixture of diastereomers. It's not a meso compound. It's not racemic. It's achiral. Right? There's no chiral center, but it's not meso. There's, again, because there's no chiral center in the whole molecule. There we go. All right, let's try number 12. 12 is kind of a weird question. This isn't on your final exam. I looked over your final exam. This question isn't on there, but I'll just go over it with you quickly. It says, what's the stereochemical relationship between these two Fisher projections? The reason why I put this question in here is I just want you to know that when you have a Fisher projection, you cannot flip it like a pancake. Okay, you can't take your hand and imaginarily put it under here and then just flip it over. You can't do that with a Fisher projection, because if you did that, all these bonds that are coming out would all be going in, and then you can't compare the two. What you can do with a Fisher projection is rotate it. Okay, so can rotate a Fisher projection. So that means you could take this compound and you could rotate this 180 degrees, right? And bring this down here 180 degrees, 180 degrees. And then if you did that, you'd end up with this. You'd have the aldehyde at the top. Then you'd have CH2OH over here. You have your two carbons, or sorry, there's three carbons, my mistake. So 1, 2, 3. And so this hydroxyl would be up here. This hydroxyl would be over here, and this hydroxyl would be down here, like that. So then I'll fill in all the hydrogens like this. So if we compare this compound and this compound, what do we see? We see that they're mirror images at the three stereocenters, right? You see the this is opposite, this is opposite, oops, and this is opposite. And so therefore, these two compounds are enantiomers of each other. Kind of a tricky question, but I've seen this kind of question on like a DAT exam for dental school, a dental school entrance exam. And so I want you to just be aware of this, especially students who might be interested in those kinds of things, is that you can't flip a Fisher projection like a pancake, but you can spin it around like a top. Okay? Try another one. Really hammering on the stereochemistry here. 3 more to go. Let's go to question 20. Let's skip ahead to question 20. Oh boy, all text. And nothing but text. Okay, so let's read it here. Question 20. It says cyclohexene reacts with bromine to give you 1,2-dibromocyclohexane. Okay. Molecules of the product would be a racemic form, and in their most stable conformation would have both bromine atoms equatorial. Racemic, and in their most stable conformation would have one bromine equatorial, one axial. Meso and meso. Well, I know the answer is not C or D, and if you're wondering, well, how did you know that so quickly? Well, remember, if we have a bromination reaction, so if we have the bromination of cyclohexene, so we take cyclohexene, and then we add bromine to it. What kind of addition does bromine proceed via? Is it a syn addition or anti-addition? Could anybody answer that? Bromination? Is it syn addition or anti-addition? Yeah, exactly. Bromination occurs via anti-addition. Right, remember, we went over the mechanism of this. You take your double bond, you have your bromine, Br2, like this, okay? The first thing that you do is you end up forming a bromonium ion, which looks like this. Okay, I'm kind of drawing it a little bit quickly here, but anyhow, so you end up with this is called a bromonium ion. like that. And then you get nucleophilic attack. So I guess I should draw these on wedges or dashes. So like this and like that. And now the bromide that's left over would come in and it would attack from the bottom face of the molecule like this, so that you would end up with a compound that looks like this, where you'd have one bromine going up and then you have the other bromine going down, but you also end up with the enantiomer. So you end up with a racemic mixture, but it's not a meso compound, so plus enantiomer. All right, so that's the mechanism for bromination. And again, it is anti-addition, because you end up with one up and one down. So anti-addition. Now, if we think about the chair here, let's just draw a chair. Pardon me, this isn't my best chair, okay? But let's say we have one bromine going up and the other bromine going down like this. Well, if the ring flips, then we're going to have one bromine going down and one bromine going up. And so both substituents are going to be equatorial, both equatorial, right? And you don't even have to draw the chair. You could just zoom in on this and say, well, if this is up and equatorial, that means that this is going to be down and equatorial, right? Because equatorial alternates up, down, right? So on and so forth. And so if we go back to the study guide, and here, let's find that problem again. Somewhere down here. It was question 20, wasn't it? Yeah. So we have racemic, and both bromines are going to and both bromines are going to be equatorial. It's definitely not meso. It's definitely not meso. And we don't have a situation where one bromine is equatorial and the other is axial. There's a lot of dots you have to connect in that one, but it's certainly a reasonable problem. Let's try another one. Question 21, right here. I'll throw this out there to my students. You guys can probably answer the questions faster than me. So it says in 21, what's the relationship between these two structures? Are they identical, conformational isomers, constitutional isomers, or stereoisomers? Anybody have an answer for this one? Excuse me. Great. My students are saying, see, excuse me, these two compounds have they have the same molecular formula, but they have different connectivity. All right, so they're constitutional isomers. Good. Let's try one more stereochemistry problem. Question 25. Excuse me. Which reaction would produce meso product? Another opportunity for us to bring up D2. Could anybody tell me what D2 is? And it's not a trick question. It's in the study guide. It's not meant to fool you. Yeah, so exactly. Coy said deuterium gas, right? So it's just, instead of using H2, they're not using H2, they're using D2. That's all. So it's just deuterium, a molecule of deuterium, D2, instead of H2. And so here we have hydration in A. In B, we have bromination. In C, we have hydrohalogenation. And then in D, we have, it's not hydrogenation, it would be deuteragenation, because we're using deuterium. But in order to get a meso product, remember, we have to have 2 stereocenters and we have to have a plane of symmetry. Could anybody tell me which one of these would give you 2 stereocenters and a plane of symmetry? Okay, let's take a look. So if we go in here, if we've got this compound and you're treating it with water and acid, that's just a hydration reaction. There's no Markov-Nikov or anti-Markov-Nikov to worry about. You just end up with this compound. So there's no stereocenters in here. So that can't be the right answer. The next one is bromination. If you take this and treat it with bromine, we just went over this, you get anti-addition. And so that cannot be a meso compound. There's no plane of symmetry in there. So that can't be the answer. The next one is treating it with HCl. That's hydrohalogenation. There's no Markov-Nikov or anti-Markov-Nikov to speak of. You get no stereocenter. But in the last one, you're treating it with deuterium gas. So remember that hydrogenation, right? When you do H2 in palladium, platinum, or nickel, right, the 2 hydrogens get added to the same face of the molecule. It's syn addition. Syn addition. But this would not be a stereocenter because the hydrogens are identical. But if you replace the hydrogen with deuterium, right? So if you replace all these with deuterium, then you end up with 2 stereocenters because you have hydrogens as well. So this is a meso compound because you have 2 stereocenters, but you do have a plane of symmetry. So we'll put here plane like that. Plane of symmetry. And so the answer is the deuteragenation, since it's syn addition, gives you a meso compound because deuterium is different than hydrogen. So it does make a stereocenter. Give me a thumbs up if that makes sense now that we've looked at it. You can see how some of these questions will challenge you, challenge your train of thought a little bit. All right, well, I think that was the last question I had picked about, about stereochemistry. Let me double check here. Let's see, did I have one more? I may have. No, that's it. So those are all the stereochemistry problems that I had picked. Let's go to the next section, which is nucleophilic substitution and eliminations. I picked a lot of problems from this one too. Son of a gun. There we go. Okay, so I thought we would start with question 1, I guess. Start with question 1. Hey, this is a good question, okay? It says, what reagents could you use to accomplish the synthesis of this compound? It's just an alkyne. So this is chapter 9. This is 1, 2, 3, 4, 5, 6. So this is 2-hexyne. 2-hexyne. Could anybody suggest, if you look at these answers, is there anyone that's a red flag to anybody? Does anybody look at any of these and just say, that's not right? That's impossible. Okay, so my students picked out D immediately. Okay, everybody smelled something rotten with D. I agree with all of you. D is a big no-no because you're taking an alkyne and an alkane, they're not going to react, right? You're not going to do an SN2. That's impossible. So D is impossible because there's no nucleophile, there's no electrophile, so there's nothing, right? You've got to have some kind of carbanion. Are there any other ones? Clinton, what's the problem with B? I noticed that you did.
There's not enough carbons.
Yeah, I agree. So let's cross that one out. So not enough carbons, right? You only have 1, 2, 3, 4, 5. So that can't work. Any other ones? Tracy says C is a problem. Tracy is correct. because Tracy says too many carbons, right? Because here you have 1, 2, 3, 4, 5, 6, 7. So that's too many carbons, yeah. Well, we solved that one by process of elimination, my friends. The only possible answer is A. And hopefully you follow me on this one. It's just a straightforward SN2 where the nucleophile comes in, attacks the electrophile, you lose the leaving group, and it's just a plain old SN2 with an alkanide. Great. Okay, awesome. Good rationale for my students. Let's try question number 6. A little more substitution and elimination. Oh boy, another question where it's just text. So question 6 says, what would be the major product of the dehydrohalogenation of 3-chloropentane by potassium hydroxide? So dehydro is a hydrogen, and dehalo, so that means you're going to be losing HCl because you're starting with 3-chloropentane. So that's the whole idea here, is you're going to take 3-chloropentane, okay, this compound, you maybe move it out of the way a little bit here, and then you're going to treat it with KOH. So I'm just going to put the hydroxide. The potassium is a spectator ion, and every single one of these is an alkene. So if you have a secondary alkyl halide, it's going to be an E2 process. Now, you've got beta protons here, and if you rip this off, okay, one of these, you form a double bond here and lose your leaving group. And so you would end up with a mixture of cis and trans 2-pentene. So you'd end up with trans 2-pentene, and you'd end up with cis 2-pentene. Now, none of these even show cis and trans. It's not even in here. And so you see that the only possible answer is D. That's the only one. So this is 2-pentene. And this is 1, 2, 3, 4. That's 2-pentene. This is 1-pentene. A and B have branching in them. That's just plain wrong. So the only possible answer here is D. There is no other possible answer for this one whatsoever. So that was another one I kind of solved by process of elimination. Let's try 9. Okay, so question number 9. It says, identify possible products of the dehydrohalogenation of trans 1-bromo-2-methylcyclohexene. So if we have this compound, we're doing dehydrohalogenation. That means we're going to be losing, oops, where's my red pen? That means we're going to be losing HBr. And so let's figure it out. Does anybody remember what the requirement is for the proton being removed and the hydrogen, or sorry, and the halogen being lost in an E2? What must their spatial relationship be? There's a word I use to describe it. If you want to do an E2, exactly, okay? So that means hydrogen and bromine must be anti-periplanar. Great, thank you. Okay, so they've got to be anti-periplanar. Now, I'm going to redraw this compound just to give myself a little more space. So the only way you can do an elimination is if the bromine is axial, right, up and axial, and the proton is down and axial, right? So let's put the methyl group in here, and we'll put the hydrogen in here. Now, if the bromine is up, because it's on a wedge, and axial, that would mean that this methyl group is down and axial, which would mean that this proton is up and equatorial. Can you do an elimination here? Yes or no? Not a trick question. I just want somebody to tell me the answer. No, impossible, right? So you can't make a double bond there. So this proton cannot be eliminated. Now, on the adjacent carbon here, you've got a proton going down, and you've got a proton coming up. Again, if the bromine is up and axial, that means that this hydrogen is down and axial. Can it be eliminated? Yes. Ergo, we can form a double bond here. So the only possible answer would be to remove the bromine and the hydrogen, the bromine and the hydrogen there, and then you would end up with this compound where you have your methyl group here, and you'd have a double bond here, like that. Now, none of the answers that they gave you even have a stereocenter, but you see that the only one that you would get is this, right? It's the only possible answer. You can't get this, you can't get this, and you can't get that. It's the only possible answer in the entire answer bank. Give me a thumbs up if you follow me on that. Even if you're saying, you know what, Mr. Beat, I got to go back and review Anti-Periplanar one more time. But yeah, I kind of see what you're saying here. All right, so you see how ACS loves to ask more than one question at a time here. That was question number 9. Let's try question number 16. So scroll down here to question number 16. Oh boy. It says here, if the alcohol is dehydrated, what's the alkene that's most likely to be formed in the largest quantity? So I'm reading question 16. This, you see that you have an alcohol and you're making an alkene. So that means that this is an elimination reaction. Okay. And yeah, it's an elimination. It's dehydration with a strong acid. So let's see if we can draw a mechanism of what's going to happen here. Now, I don't have a ton of space on here, so I'm going to use a bond line structure for the starting alcohol, which is going to look like this. This is the starting alcohol, okay? This compound that I just drew is this. All right, now what are we going to do if we're in a strong acid, sulfuric acid? The first thing we're going to do is we're going to protonate this and convert it into a good leaving group. So the leaving group is going to leave, and then I'm going to end up with this. So I have my tert-butyl like this, like that. Now, what's going to happen now that I'm at this secondary carbocation? Can anybody tell me? Once I have this secondary carbocation, what's going to happen? Will anything happen, or I'm going to have a methyl shift, aren't I? Because this is a secondary carbocation, but if it undergoes a methyl shift, this, then you end up with a tertiary carbocation, which is going to be more stable. All right, now you had this proton here all along. It never went away. And so now you're going to form the most stable alkene that you can by eliminating that proton and forming a double bond here. So you're going to end up losing that proton. I'm not going to draw the whole mechanism for that, for the proton transfer, but you're going to end up losing that proton and you're going to form the double bond here. So you're going to end up with this compound. Now, which one of these is that compound? Could anybody identify it? Could anybody identify this compound from A, B, C, or D? Yeah, it's B. Exactly, it's B. All right, and there you have it, my friends. That's it, that's all. Okay, so make sure you know your elimination. All right, this is an this would be an E1 reaction. So E1 elimination. It's one of my favorite reactions. It's so cheap. You just take an alcohol and you heat it up with a strong acid. It doesn't get much less expensive than that in organic chemistry. Let's try question 17. So next one. Oh boy. Well, this is just kind of a straightforward, do you understand mechanisms? Sometimes students will ask me, well, look, if I want to take an MCAT, that's a multiple choice exam that could have organic chemistry. Why do I have to spend so much time practicing mechanisms? Well, number one, you have to know them because of questions like this. They're asking you if you're taking cyclohexanol and dehydrating it. So if you take cyclohexanol, which is just this alcohol, and you treat it with sulfuric acid, and you end up making cyclohexene, right? Because that's what dehydration is. You end up losing water. You form this. Well, what's the first step going to be? Could anybody tell me? And it's not a trick. We looked at it in the last problem. That, yeah. Oh, yeah. Okay, good. The answer is D. The first step is going to be protonation of the alcohol to convert it into a good leaving group, right? So that enables it to leave once you've formed a good leaving group. So the first step in dehydration would be the protonation of that alcohol to make it a good leaving group. So we'll put here convert poor leaving group into good leaving group. Great. All right, let's try a couple more here, and then maybe we'll take a break. So question 20. Oh boy, another mechanism, question here. This is question 20. Let's read through it together. It says, which of the mechanistic steps shown is not a reasonable one in the mechanism to describe the formation of this compound, 2-methyl-1-butene, by the dehydration of this compound? So all they're saying is, look, you can take this compound and make this compound from it. There's a mechanism associated with it. Which one of these steps is not reasonable? Is there any one of these mechanisms that just looks a little wacky to you? I'll throw that out there to my students. You could examine them. Is there any mechanism here that just you're like, that doesn't look reasonable? I can't imagine why that would happen. I'd say that B is okay because you're making a tertiary carbocation, right? In B, you're going from secondary to tertiary, so that seems reasonable to me, that hydride shift. D looks weird. Well, D is okay as well because you need to make a double bond here. It's not saying that this is major product. This is, I can tell you right now that this is not the major product. It's a product, but it's not the major product. So don't be fooled by that. They're telling you that that is a product, and this is the only way to make that. So D looks good, B looks good. Is there one here that you're just like, oh, I don't like that? In A, sorry, go ahead.
I was gonna say in C they just made up a hydrogen, right?
No, there's no hydrogen made up there.
Well, it's CH2 on this. It's CH3 on the product side, and then it's CH2 on the reactant side. But it wasn't there. Oh, it was there. I was looking at the wrong thing. Never mind.
Oh, no worries, no worries. So what they're doing here is they're showing you this hydrogen explicitly. So this is a hydride shift. Technically, there's nothing wrong with this step, but you're making a primary carbocation, which is really unstable, number one. And if you were to make a primary carbocation, that would be to make a double bond somewhere over here. Okay? And there's no double bond there. So this is the correct answer. There's no reason to make that primary carbocation. I mean, this is just the protonation and loss of leaving group. So that's perfectly reasonable. So the answer is C, because you don't make a double bond on the end there that I have with the red oval around it. There's no reason to make a primary carbocation. Very unstable. All right, we'll try a couple more here. So that was 20. Let's go skim all the way down to 30. Really getting into it here. I'm going to skip 30. I don't have any questions like 30 on the exam. Let's do 31. 31 is a great question. It's about nothing more than an E2 reaction. It says, if you had this substrate, so this here, if you have C2H5ONA, that's the same thing as NaOET, right? Because C2H5 is the same thing as an ethyl group. That's all they're saying here. So you have sodium ethoxide, you have a tosylate, which is a good leaving group. You do an elimination. Which one of these is the right mechanism for an elimination? Is there any of these? I mean, number one, could anybody answer this? Hopefully you can, because we did many E2 eliminations. But there is, I just skimming these here while I'm talking, and there's a couple of mechanisms that are just totally way out in left field. And I mean, like, just completely wrong. Are there any mechanisms that just look, oh no, this is not good? Any mechanisms that just look totally wrong to you? I agree, Michelle. B looks really funny, doesn't it? Why in the heck would you be drawing a curved arrow starting on an atom and then going to a negative charge like that? That's impossible. So that's a big no-no. Also, this is a leaving group. I don't even know what the hell is going on here, so I can't even, you know, that just looks wrong. Any other things that look wrong to you here? Remember, E2, if it's E2, that means together. Okay, that means that all the steps, exactly. Thanks, Tracy. Right, what they've drawn here, this is an E1, is what they've drawn, so that's not an E2. All right. What else? What about C? This is just plain wrong. Why would the ethoxide attack a carbon that's not even electrophilic? I mean, E2 is this. It's where you rip off a proton, form a double bond, and then lose your leaving group. This is the proper E2 mechanism. This has, I mean, this arrow is incorrect. I mean, this thing is just totally crazy. This is wrong. This is wrong. So there you have it, my friends. Let's try one more and we'll take another break. Let's try question number 32. Oh boy, stereospecificity. Aha. We need to do a problem like this. Okay, very important. So I'm not going to review anti-periplanar. We've gone over it already today. Requirement is that the bromine and the hydrogen must be anti-periplanar in order for this elimination to occur. So what I'm going to do is I'm going to move the hydrogen over here. I'm going to move the methyl group down here, and I'm going to move the phenyl, C6H5 is a phenyl. I'm going to move that up here. So I'm going to redraw the compound the best I can. So I've got my methyl group up here. I'm just going to write C6H5 as pH because it's easier for me. I'll put my bromine up here. So now my hydrogen is going to be anti-periplanar. I've got my phenyl up here, and I've got my methyl down here. So now, if you're looking down here with your eyeball, you can see that the bromine and the hydrogen are anti-periplanar to each other. And so if the base, my hydroxide, ends up doing the E2, so ripping off the proton, forming a double bond, losing the leaving group like that, what do I end up with? I've got my double bond like this. Okay, got my double bond that way. I've got my methyl group coming up here. That's this methyl group. I've got this phenyl coming down here, like that. I've got this phenyl going up in the back, like this. And then I have the other methyl group coming down like that. So I end up with the E compound, which is C. That is the E alkene that I'm looking for. And that's it. Another thing you could do is you could look down the Newman projection. So if you want to draw the Newman projection, you could totally do that. You'd have the bromine here. You'd have the phenyl in blue here. Then you'd have the methyl group in green up here. In the back, you've got the hydrogen, that's anti-periplanar. Here, you've got the phenyl in red over here, and then you have the other methyl group coming down like that. So when you form the double bond in between this carbon and this carbon, the carbon in the back, you can see how these two are on one side and then these two are on the other, but the phenols are going to end up being trans to each other. Give me a thumbs up if you follow me on an elimination that is stereo specific. All right, stereo specific E2 is what that is. All right, only one possible answer in this case.